All right, this is the day 46 lesson of AP Chemistry. The unit that we are now on, Unit 4, has to do with thermochemistry, and that's simply the study of heat going into and coming out of chemical reactions and other chemical processes. There's a lot of vocabulary involved in this, so this first day is really a lot of basic vocabulary development for this subject. And then there is an important equation that we're going to do. It's a fairly long assignment, but it's straightforward as far as getting the information from the notes. So what I'm going to do is read the notes to you and go over the problems or go over the questions that I've given you. All right, so let's get going on this. Energy is defined as the capacity to do work. You can think of it as just the flip side of work. So you put gasoline in a car, that's energy, because you want that car to do work, which is move. And both energy and work are defined by, or use the units of measure of joules, Joules, and that's the common unit of measure. So they're basically both the same thing if they both use the same unit of measure. Now, energy in a chemical equation can cause an object to move, that's actually do some work, abbreviated small w, or produce heat. And heat in chemistry is abbreviated by the letter Q. The change in energy is the sum of these two together. So you can change energy either by, you can increase the energy in a chemical system either by increasing the heat or by doing work on it. In chemistry, work is defined as pressure times the change in volume. So if you have an amount of pressure pushing in on the chemical reaction and the volume expands, and that's the work that it's done. If there's no pressure pushing in on something, then there's no work done. The reason it's negative we'll get to in a short while, why that's a negative pressure times change in volume. So it's constant pressure, and that would be, for example, atmospheric pressure, like the atmosphere in the room that you're working in or studying in, times the change in volume. All right, so W equals negative P delta V, where V is the volume of the container and P is the pressure pushing against a movable piston. So we talked about what a piston is today. Work going out of the chemical reaction is defined as negative. So that's what it means. It means the chemical reaction is pushing outward on the environment around it. So that's the answer to question number 2. So you can have your questions right there by your side. What are the two ways energy can be absorbed or released by a chemical reaction? It's by either doing work, that is making something move, or by releasing heat. Question number 3. Okay, so let's keep going on that. So work can never be done with 100% efficiency. That means that all the gasoline you put in your car does not go towards making that car move. A lot of it is burned off as wasted heat. If you feel the engine of a car after someone's driven it, it's very hot. And that's not useful. That's not a useful or a good efficient use of the energy, the gasoline. But the fact is, no engine is 100% efficient. So this means that some heat will be lost whenever work is done. It is possible, however, to release all of the energy in a chemical reaction in the form of heat. For this reason, it's preferable to study heat released or absorbed by a chemical reaction as a way of studying the energy of the chemical reaction. So to continue with the car analogy, I can't measure the amount of energy in the gasoline by how far the car moves, because a lot of that gasoline will be dissipated off as wasted heat, and not all of it goes into making the car move. I can, however, measure the amount of energy in the gasoline by measuring how much heat. If all I do is turn the engine on and let the car just sit there and idle and don't move it, then I know 100% of the gasoline went into heat and none of it went into work. And that's why we study heat coming into or out of a reaction, because it's something we can isolate. So energy can be divided into two types, potential and kinetic energy. Now, these have different meanings in physics. You've talked about potential or kinetic energy. So kinetic energy is simply the energy of anything in motion. Potential energy is energy that's stored, that can be turned into kinetic energy, but hasn't. So potential energy is stored energy that can be released. In chemistry, potential energy is stored in chemical bonds. A lot of times that's what we want a chemical reaction to do, is to give us energy that's stored in those bonds. That's why we burn hydrocarbons for fuel, for energy, to either make cars move or to just heat the room, is because they store a lot of energy, and if we can get the chemical reaction, the hydrocarbon, to break those bonds, it will release that energy. Kinetic energy is the released energy of motion. So what that is in chemistry, the kinetic energy is the motion of atoms or molecules. We talked about that in gases. Gases have molecules and atoms that can freely fly around in a container, and that would be kinetic energy. That's the definition of temperature that we're just about to get to. But it can also simply be in a solid. It can be the atoms or molecules wiggling back and forth, or rotating or turning, or any kind of motion that they have. Even though they can't move anywhere, they can still wiggle back and forth, and that is kinetic energy as well. So that's the answer to question number one. Explain what potential and kinetic energy are in terms of a chemical reaction. And we also answered question number 3. Why is it preferable to study heat rather than work as a way of understanding the energy of a chemical reaction? Because we can isolate heat. If we don't allow any work to be done, then all of the energy coming out of a chemical reaction is going to be in the form of heat. So we can directly measure how much energy is in that chemical reaction. Okay, so temperature. We talked about temperature when we were talking about gases. So temperature is the kinetic energy of atoms or molecules. More technically, it's the average kinetic energy of the atoms or molecules in either a solid, liquid, or gas. Although the particles in the solid can't move around, they can have kinetic motion energy by vibrating in place. Heat. Now, what is heat? What's the difference between heat and temperature? Heat is the transfer of energy. So heat is a form of energy. It's measured in joules, as all energy is, and it's the transfer of energy between two objects of different temperatures. So if we have something here, just draw a quick example. A block of iron that's 500 degrees centigrade. And really, let's use Kelvin, because Kelvin is the absolute temperature scale, so 500 Kelvin. That represents how much energy the molecules, the iron atoms inside that block of iron have. But that's not heat. It's internal to the block of iron. So that's the temperature. If I take a second block, it can be iron or something else, or it could simply be the atmosphere, the air. And it's at a lower temperature. So that's 100 Kelvin. And I put them in what's called thermal contact, which basically means I put a piece of metal in between them. Then what will happen is the heat, which is Q, will flow from the hotter object to the colder object. It's just like when you drop an object, it falls from higher potential energy down to the floor, which is at lower potential energy. You never drop something and have it fly up to the ceiling. Similarly, you never have heat go from the lower temperature to the higher temperature. So it's the same kind of thing. So again, think of temperature as being internal to the object, and think of heat as being an external flow that's either into or out of an object, just depending on whether the object is hotter or colder than the other object, or than the atmosphere, than the air that it's in. All right, so the kinetic energy of in one object transfers heat energy to increase the kinetic energy of another object. And this will happen until the kinetic energy in both of these objects, assuming none of this heat is lost to the environment around it, this will happen until the kinetic energies of these are the same. That is to say, the temperatures are equalized. The unit of measure for energy, heat, and work, and all three of these are measured in joules. For example, we want a car to do work of moving us. To do this, the car must have stored energy called gasoline. So we talked about that. All right, so in chemistry, a calorie is also used to measure energy, and 1 calorie is 4.184 joules. Now, the kind of calorie that you read on a food wrapper, like a bag of potato chips or something, is actually 1,000 chemistry calories. So if a bag of potato chips says it's 250 calories, that's food calories. That means it's 250,000 chemistry calories. So it's just simply a renaming. And the food calories, by the way, use a capital C, whereas chemistry calories use a lowercase c. All right. So there's some terminology you need to know in studying thermodynamics, and it's pretty straightforward. So analysis divided into two spaces. The system is what we're analyzing. It's what we're interested in. In other words, it's the chemical reaction. That's called the system. It's what we're actually studying in studying a chemical reaction. It could be a single atom, or it could be a single atom, or it could be a container of substances. For our purposes, the system is where the chemical reaction takes place. Okay, now the surrounding. Surrounding is everything outside of the system. So as far as we're concerned for the study of a chemical reaction, there's only two things. There's the system, and then there's everything that's outside of the system called the surroundings. Closed systems can exchange energy but not matter with the surroundings. And that's typically what's happening in chemical reactions that we're dealing with. What's inside of your beaker causing a chemical reaction is going to stay inside the beaker, but what can come out is the heat. The heat can come off of that. These are the systems that we will use. Open systems can exchange both energy and matter with the surroundings. And in our lab, we hope that doesn't happen, because that means your chemical reaction splatters all over the place. We don't want any of the matter, any of the chemicals to come out of the beaker, but that's what an open system is. Isolated systems are basically sealed in a container and in an insulated container, and they cannot exchange either energy or matter with the surroundings, such as a thermos. When you put hot coffee or something in a thermos, it keeps the liquid hot. Neither the liquid nor the heat from the liquid can come outside of the thermos. Now, if you take the system and the surroundings together, that's referred to as the universe. Any energy that leaves the system must enter the surroundings, and any energy going into the system must have come from the surroundings. So as far as energy is concerned, there's only two places. It's got to go one way or the other. It's got to go from system, surroundings, or from surroundings back to system. That means that the energy, we can have a simple expression here, a simple equation, that the energy going into the system is equal to the negative energy of the surroundings. In other words, energy going into the system is equal to energy coming out of the surroundings. And you could also flip that negative sign to the other side. Any energy coming out of the system is going to be going into the surroundings. The first law of thermodynamics states that energy is conserved, which means that energy is not created or destroyed. And just as we talked about conservation of mass, where matter cannot be created or destroyed, the same is true of energy. Energy can be converted from one form to another, such as heat, electricity, or mechanical. And we talked about this relationship already. However, in chemistry, when we talk about energy, as far as this level of chemistry, we're purely interested in heat energy at this time. So delta E is the change in energy, Q is the heat added, and W is the work done on the system. So the convention for the signs, convention just means the way it was decided to be done, is that you think of it like a bank account, putting money into your bank account. If you put money into a bank account, it's positive. And if you take money out of the bank account, you withdraw money, it's a negative. So when work or heat are put into the system, the number is positive. So there you got heat and work going into the system and into your chemical equation, that's positive. When work or heat are removed, then that's a negative number. So there's heat and work coming out of the chemical reaction. Okay? So as I say, we're hitting you with a lot of vocabulary here. It's just kind of almost like a glossary to a textbook. All right, so when heat enters a chemical reaction or a system, it's called endothermic. It's going in. And when heat leaves the chemical reaction, it's called exothermic, like exiting a room. It's exo. A state function, and this is something we don't really deal with a lot, but it is a formal definition that they give you, and it has significance in other areas in later chemistry, but we don't really deal with it, but it is a definition you should know. A state function is a function that only cares about the value you end up with at the end and not how you got there. So internal energy is a state function. And what that's basically saying is this. It's saying that you could increase the energy in a chemical system by either increasing the heat or by not increasing the heat at all, but increasing the work. or some combination of those two. So how you get to that energy change, that increase in energy, could be any combination of Q plus W. State functions are capitalized letters, whereas non-state functions like heat or work are lowercase letters. Okay, and the example that we used in class, if you begin a walk at 0 feet above sea level and end up at the top of the hill 1,000 feet above sea level, it doesn't matter what path you took, your elevation change is 1,000 feet. So in terms of the elevation, that's a state function. You're going to end up 1,000 feet higher. How you get there, whether you go up and down a lot of hills or whether you just go straight up a path to the top. However, the distance you walked to get from that bottom to the top of that hill is not a state function. You could have walked a really windy path or you could have walked a very straight path. So distance is not a state function. In other words, you could have walked 2 miles to get to the top of that hill, or maybe just 1 mile if you took a different path. But the elevation change is going to be 1,000 feet no matter what. Another example, in one case, you heat water to 100 degrees and cool it to 50 degrees. In the second case, you cool the water to 0 degrees and then heat it to 50 degrees. The only thing that matters is the final temperature of 50 degrees. So temperature is a state function. Okay, if a system produces 1,000 joules of energy, it could be by putting out 600 joules of work and 400 joules of heat. It could be done by putting 100 joules of work and 900 joules of heat, or any combination of heat and work that add to 1,000 joules. So energy is a state function, but heat and work are not state functions. So the state functions are the ones we talked about with gas laws, at least temperature and pressure, and then now energy. Those are all capitalized letters when you write them. Work and heat, which is small w and small q, are not state functions. Okay. Let's move on to the next topic, and this is something you're familiar with, and this is solids, liquids, and gases, and I'll fix this in your permanent notes. So solids, liquids, and gases are called states of matter. They're also called phases, but in this case, we're calling them states of matter. So states of matter determine how atoms and molecules connect to one another. Solid atoms and molecules are in fixed positions. So for example, right here, these molecules can't move. They can wiggle back and forth. They can have kinetic energy. They can wiggle around, they can twist, they can do all kinds of things, but they can't break away. So they're rigid. They have a very fixed shape. When you have an ice cube, it's usually square, okay? And they have a fixed volume. That ice cube takes up a certain amount of space. So solids, the way it's typically said is that solids have fixed volume and fixed shape. Now, liquids are not rigid. You can slosh them around in the glass. You can slosh water around in the glass. It has no fixed shape, but it does have a fixed volume. In other words, if you have 1 gallon or 1 gallon of water, you can pour that into different containers that have different shapes, but it's still 1 gallon of water, so the volume does not change. By the way, just as with solids, they cannot be squashed, as they say here. You can't compress them is really the more technical way to say that. They can't be compressed or squeezed down. Finally, gases, what we finished talking about last week, they have no fixed shape and no fixed volume. So I could have a bottle of really strong perfume, a really small bottle that fits in my hand. So all those perfume molecules fit inside of that bottle and they take on the shape of that bottle. If I open the bottle and that perfume, it's a warm day, that perfume comes out, those molecules will fill up the entire room and they'll take on the shape of the room. So they have a larger volume than they had when they were in the little bottle, and they also have a different shape than they had when they were in the little bottle. Now, gases can be compressed, okay? We've talked about that. You can decrease the volume or increase the volume of gases. All right, so liquid molecules are attracted to each other but can move. Example, water. Gas molecules are detached from one another and move freely. So example, steam or just air is another good example. Solids have the least amount of energy. That's why they stick together, because they don't have a lot of energy to break away from each other. And gases have the most energy. They have enough energy for their atoms and molecules to break away from each other. All right. Enthalpy. Now, this is a term you're going to be hearing in your dreams for the next week or so. In fact, it's a term that we're going to be talking about throughout the rest of this course. So let me just give you the quick definition of enthalpy. It's heat. That's what it means. It's just a fancy chemistry word for the heat, that specifically the heat that goes into or comes out of a chemical reaction. So enthalpy is the amount of heat taken in or released by a chemical reaction under constant pressure. What does that mean, constant pressure? Well, if you're doing an open air experiment in our chemistry lab and you have an open beaker, the pressure on that chemical reaction is the atmospheric pressure, which we've said at sea level is about 1 atmosphere. And that's not going to change. So that's what it means. It means it's an open air experiment. That's the way to think of constant pressure. As opposed to what? As opposed to having something in a sealed container where you could have, say, an explosion inside that sealed container that doesn't blow up the container, of course, but the explosion causes the pressure to greatly increase inside the container. So that's not what we're talking about. If that's the case, then the definition of enthalpy changes, but you really are never going to be asked about that. You're just going to be asked about enthalpy as being heat. So basically, this equation is the one you want to think of. So delta H and enthalpy, let's go ahead and finish reading this. In chemistry, we're interested in changes in enthalpy that take place during a chemical reaction. Change in enthalpy is represented by delta H. So delta H equals Q. So remember we said heat was. Heat is not something that's internal to an object. It's the amount of energy that's coming out of that object or going into that object during a chemical reaction. So delta H just simply represents that amount of heat that's going out or coming in. It's the change in enthalpy, which is inside of the reaction. So what happens inside of the chemical reaction in terms of heat? When some heat goes out, that's called the change in enthalpy. Okay, heat going into a chemical reaction is positive. That's endothermic. Remember we talked about the bank account. So heat goes in, it's like putting money into your bank account. That's positive. Heat leaving the reaction is negative. That's exothermic. The enthalpy related to turning a solid into a liquid. So now we're going to get into some special types of enthalpies. So think about turning a solid into a liquid. So think of ice melting. Now that's not a chemical reaction. We mentioned that in class. That's a physical reaction. Because you had H2O before, ice is made up of H2O molecules, and liquid is made up of H2O molecules. So that's not a chemical change. It's just that the molecules gained energy and they were able to break apart from each other and become more energetic, that is to become a liquid. Whereas when they were less energetic, they stuck together really tightly as a solid, as the ice cube. So the enthalpy of ice melting is called the enthalpy of fusion. So what causes ice to melt? Heat going into the ice cube. So remember the bank account, that would be a positive enthalpy of fusion. If heat goes into the ice cube causing it to melt, that's positive enthalpy. If heat comes out of the ice or out of the water, then what that's going to do is lower the energy inside the water, and that's going to cause the water molecules to stick together, and that's going to be a negative enthalpy of fusion, and that's when water turns to ice. So energy comes out of the water, it causes the water molecules to stick together, and that turns the water into ice. So that would be a negative enthalpy of fusion. Similarly, for boiling water, if the enthalpy related to turning liquid to gas or gas to liquid, that's called the enthalpy of vaporization. So turning water into steam or vice versa. So think about that. What would be a positive enthalpy of vaporization and what would be a negative enthalpy of vaporization? Well, if you have water and you put heat into the water, you increase the enthalpy of the water, so that's positive. That's going to cause the water to turn to steam because you're putting more and more heat in. It's giving the water molecules more energy. They're able to break away from the water and start floating away into the air, into the atmosphere. And so that's a positive enthalpy of vaporization. If you take the energy out of the steam, and that's what happens when you see condensation on leaves, and the term for that is condensation. That's when the steam or basically vapor turns back into droplets of water or to liquid water. Then that would be a negative enthalpy of vaporization because heat is coming out of the water molecules and they're condensing together to form liquid water again. So heat of fusion, heat of vaporization. Okay, so the letters after each product and reactant reflect the state of matter. There are 4 possible values that can be displayed, and you've become familiar with these already. We've certainly dealt a lot with aqueous and solid, and now you're going to be dealing with gases a lot and with liquids. Remember, a liquid is a pure liquid like water. It's not a solution like salt water. That's not considered to be a liquid. So the states, liquid, gas, or solid, of the products and reactant affect the enthalpy values of the reaction. Another couple terms to know in chemistry that are used from time to time. You're not going to hear these a lot, but you will hear them some, and they might even test you on these. An extensive property is a property that depends on the amount of matter being used. An example would be mass or volume. Okay, so the mass of a substance or the volume of a substance depends on how much of it you have. Another thing that would be an extensive property would be how much heat it takes to warm up a block of iron 10 degrees. If you have a big mass of iron, a huge iron block, it's going to take a lot more heat to heat that massive iron block up 10 degrees than if it was just a little tiny block of iron. So the amount of heat that's required to increase the temperature is an extensive property. It depends on mass. An intensive property is a property that's independent of the amount of matter. Example would be density. So a piece of wood, whether it's a small piece of wood or a large piece of wood, is going to have the same density. It's going to float on water because they have the same density. And we'll talk about the relationship between density and water and whether things float or sink. But in other words, density is an amount of mass per unit volume. So if you double the amount of volume of that substance, you're going to double the mass. If you triple the amount of volume, you're going to triple the mass. So the relationship between mass and volume stays the same, whether it's a big piece of wood or a small piece of wood, whether it's a big piece of iron or a small piece of iron. An intensive property does not depend on how much of the substance you have. An extensive property depends on how much of the substance you have. And we'll see some examples of that coming up that'll make that clearer. So here are the rules for enthalpy. All right, let me get you right there. Okay, so enthalpy depends on the amount of reactants and products, and that makes it an extensive property. So again, if you want to take, if you have twice as many moles of in a chemical reaction, it's going to have twice the enthalpy. It's going to give off twice the amount of heat. So enthalpy is an extensive property. It depends on how much of the substance you have. The enthalpy of a reaction is the same as the enthalpy of the reverse reaction, but with the opposite sign. So that was the example I was giving you with ice and water. Okay, the enthalpy to turn ice into water is positive enthalpy of fusion because you have to put heat into the ice cube to make it melt into water. If you want the water to freeze back into ice, you have to take out that exact same amount of heat. So it has the exact same enthalpy, but it's a negative sign. So the number is the same, but the sign is different depending on whether you're putting heat in or taking heat out. And number 3, enthalpy depends on the state, liquid, gas, or solid of the reactants. So if you have a chemical reaction, 2H2 plus O2 gives you 2H2O. It depends on whether you want that water that you're going to produce in that reaction to be a gas or a liquid. The enthalpy is going to be different depending on whether you want it as a gas, which has more energy in it, or whether you want it as a liquid, which has less energy in it. And you'll see some numeric examples of that coming up, so don't worry about that too much. But the enthalpy to turn liquid water into gas or steam is 88 kilojoules per mole. So this is a unit of measure you'll get used to seeing. It's 88,000 joules of energy for every mole of the substance. So if you have 2 moles of the substance, you'll need 176,000 joules of energy to make that happen for 2 moles of the substance. You just have to double everything. An object or a chemical reaction are specific heat capacity or specific heat. So specific heat tells us how much the temperature of a substance will change when a certain amount of heat is put into or taken out of the substance. So specific heat capacity sometimes just called specific heat, is defined as the amount of heat required to raise 1 gram of a substance by one Kelvin. Now, heat capacity, in other words, the same thing but without the word specific, is the amount of heat required to raise the temperature of some unknown mass. In other words, whatever amount that you have by one Kelvin. Or another way to state it is this, that it is the specific heat of the substance multiplied by the mass of the substance. So getting back to our terms extensive and intensive property, heat capacity is extensive because it matters how much of the substance that you have. Specific heat capacity is intensive because it's defined as the amount of heat per gram. So that's never going to change for a specific substance such as iron or such as water. So again, heat capacity is the amount of heat needed to raise the temperature of whatever amount of that substance you have by 1 Kelvin. Specific heat capacity is defined as the amount of heat required to raise exactly 1 gram of that substance by 1 Kelvin. So specific heat capacity applies to a substance, whereas heat capacity applies to the entire mass of the object that you're measuring. So that depends on what it is you're actually measuring and how much of it that you have. Okay, let's talk about the relationship between heat and temperature, and there's a really important equation related to this. So the formula for converting a temperature change to an amount of heat is the following. Okay, so this formula right here. So the amount of heat that you will get from an object or from a chemical reaction is equal to the mass that you're dealing with. Obviously, the more mass, the more heat you'll get, times the specific heat, which is a characteristic of the substance, times the change in temperature. So if the temperature goes down, then the amount of heat that you get out is going to be greater. So the temperature goes down, the heat is going to come out of the object, okay? So that's going to be a negative Q if the temperature goes down. So the delta T means that the final temperature is lower than the beginning temperature. That means delta T will be negative, so Q will be negative. And remember, when Q is negative, it means the heat comes out of the object. So if the temperature of the object goes down, it means that heat must have been escaping from that object. You can think of it in the other direction. If the temperature goes up, so the final temperature is greater than the initial temperature, then that's going to be a positive number, and that means Q will be positive. So that means that heat went into the substance or into the object. Okay? Now you can just rearrange that equation and solve it for temperature. So if you want to know how much change in temperature you're going to get, if Q is positive, that means heat is going into the objects. Just think of it an iron block. You divide it by the mass and the specific heat of iron, and that'll tell you how much the temperature changed, and that'll be a positive number. So that means the temperature will go up if you put heat in, and that makes sense. So if delta T is negative, then Q is negative, and the reaction is exothermic. Heat went out. If delta T is positive, then the reaction is endothermic. So think of touching a cup of water sitting next to an iron bar on a normal morning. The cup of water will be cool and the iron bar will be really cold. Now it's 1 p.m. and you touch the same cup of water and the iron bar. The water will be warmer, but it's still not hot. It's just a little bit warmer than it was in the morning. The iron bar, however, will be very hot. So the water seemed to change its temperature a little bit, but the iron bar changed its temperature quite a bit. It went from very, very cold to very, very hot. That's because water has high specific heat. And therefore, an amount of heat going into water will not change its temperature very much. So the same amount of heat going into water that allows its temperature to stay kind of the same, going from just cool to warm, that same amount of heat going into an iron bar, which has a low specific heat, that will cause the iron bar from going from very cold to very hot. So let's work an example here. So let's say we can use this equation to see how 1 gram of each of the substances will change if 10 joules of heat is added. So we've solved both of these equations for T. So if you put in 10 joules of heat, water has a specific heat of, of 1 gram of water. Water has, this is iron, I'm sorry. 1 gram of iron. Iron has a specific heat of 0.45 joules per gram Kelvin, and we'll talk about the units of measure in more detail. So iron has a low specific heat compared to water, which has a specific heat about 10 times greater, 4.18. So if you do the math on that, you get a temperature change in the iron of 22 degrees. By putting 10 joules of heat into the iron, the temperature went up by 22 degrees. On the other hand, for water, if you put the same amount of heat in, given that it has this higher specific heat, the temperature only goes up by about 2 degrees. So that explains why the water didn't get a lot hotter. It was cool in the morning and warm in the afternoon, whereas the iron bar was very cold in the morning and very hot in the afternoon, and it's because of the difference in the specific heat. So the same amount of heat added causes the temperature of iron to rise almost 10 times as much as water, which explains why the temperature extremes in iron are much greater. Substances with low specific heat values will experience greater temperature changes when heat is added or removed. Also, small changes in temperature of these substances will take in or release larger amounts of heat. So specific heat is an intensive property because it does not depend on the mass of the substance. And I kind of ended the notes there, and you will get a full set of the notes. So now you can go ahead and answer the question, and we can do that. And I'm not going to write them all out. That will take forever, but let's just go over. I will actually go ahead and work some of the problems that they give you. So let's go over what the questions are. So explain potential kinetic, that's in the notes. All of these are in the notes. So the idea of these questions is just to get you to read the notes and write out the explanations. If, however, one does not make sense, then bring it up in class, okay? Explain the meaning of system, surroundings, and universe down here. So that's in the notes. Explain when heat and work are positive or negative. That's in the notes. So all of these questions are in the notes. Just go ahead and read the notes. They're pretty straightforward answers. Okay, here's something about state functions in the notes. Define solid, liquid, and gas. That's in the notes. What are solids, liquids, and gases referred to as, or as what are they referred to? That was maybe a little bit unclear what that was asking for. They're called states of matter. So we'll fill that one in. Okay, define enthalpy. Enthalpy is simply heat that comes into or goes out of a reaction at constant pressure. Define enthalpy of fusion and vaporization. That's in the notes. We talked about that. Chemical changes occur when the substance has undergone a chemical reaction. Physical changes occur when the same substance changes state. So water is still water, whether it's ice, liquid water, or steam, it's still water. That's a physical change. Extensive and intensive properties are down at the bottom here. So we're moving on. You can do these on your own. What are the rules for enthalpy? So I gave you those 3 rules of enthalpy. What is heat capacity and what is specific heat? What is the formula that relates heat gained or lost by chemical reaction and the temperature? So that was just Q equals M, mass of the amount of mass that you have, the specific heat of that particular substance, and the change in temperature. So that's that point. It's the only formula we've dealt with. Okay, this wasn't explicitly dealt with in the notes, but you'll remember something that we talked about in gas laws, assuming that these are all gases, and it was this. If we take P, V equals N, RT, what it means is if we increase the number of moles, we're going to increase the volume. In other words, more molecules is going to push the balloon bigger, right? It's going to make the balloon push out wider, and it's going to be bigger. So if you increase the number of moles, number of molecules that you have, you'll increase the volume. So what you do in this chemical reaction is you simply count how many moles you have on either side. So here you have 2 moles of SO2 and 1 mole of O2, of oxygen. So that's a total of 3 moles of reactants. After the reaction, you have 2 moles of product. So you went from 3 moles down to 2 moles. So does the volume of the container increase or decrease? It decreases. Because you have fewer moles, you have less volume. So the balloon got smaller. So in other words, you put these two together to form that. Now you may say, well, wait a minute, you got twice as much stuff here and you only have one thing here. But these two get put together, these two have twice as many particles. There's 3 particles here for every 2 particles there. So it's 1.5 times more particles on the reactant side than the product side. So since you have, the bottom line is, since you have more moles here than on this side, that means when you decrease the number of moles going over here, you also decrease the volume of the container, okay? So that's a decrease. Okay, a gas expands from 0.5 liters against an external pressure of 0 atmosphere. How much work is done? So work equals pressure minus pressure, negative pressure, delta V. So that equals, there's no pressure. So 0 times the change in volume. It went from 0.5 to 2.5, so that's 2 liters. So that equals 0. If you're not pushing against anything, you're not doing any work. So that's really the thrust of that problem. Okay, a gas expands from 0.5 to 2.5 against a pressure of 1 atmosphere. What will the work be in liter atmospheres? What will the work be in joules? All right, so we've never made that connection. So, and that's actually in a later part of the notes that I'm going to give you. So let me go ahead and give you. Okay, so it says a gas expands from 0.5 liters to 2.5 liters against a pressure of 1 atmosphere. So what is the work in liter atmospheres? So if the gas is expanding, it's pushing out against the surroundings, and therefore it's going to be negative work because the work is going out of the system and into the surroundings, and that's what's implied by the gas expanding and pushing outward. So we simply use our formula for work, which is W equals negative P delta V. The pressure is 1 atmosphere. And the delta V is 2.5, that's the final volume, minus 0.5 liters. So that's going to be 2 liters. And so that's going to be work is going to be, and that should be negative there, it's going to be negative 2 liter atmospheres of work. Okay, now, how does that convert to joules? That is something that wasn't in the notes, so let me give you the conversion factor. And the conversion factor is 1 liter atmosphere is equal to 101.3 joules. Okay, so they're both units of energy, because joules is energy, liter atmosphere is energy. All right, so let's just do the conversion then. Negative 2 liter atmospheres times 101.3 joules per 1 liter atmosphere. And that's going to equal 202.6 joules. And it's negative because it's pushing out against the surroundings. So anything inside the system does work pushing out away from the system, that's going to be a negative. All right, so that's the answer to that one. If 29, if delta E equals Q plus W, can you tell whether delta E is positive or negative in the question above? Well, we don't know anything about the heat in that, but we're going to say that it was a negative because it was expanding. So that's the point I was making there. So delta E, since the energy is going out of the system, out of the chemical reaction or the object, delta E is negative. because energy is leaving the system. Okay, number 30. 30 and 31 actually were part of another question, and I'm going to eliminate those. So we'll take those up when I have the complete question with that. So go ahead and scratch those. Those were left over from another question. Okay, let's go to 32. Now your copy has numbers all along here. It shouldn't. That was just the numbering. So this is the equation we're dealing with. So measuring heat, formerly measured in calories, is called calorimetry. And now we measure heat energy in joules. And we're going to use this equation. So now we're going to have a chance to work through some of these work through this equation a few times. Okay, so the formula is Q, which is heat energy, so that's measured in joules. Mass is measured in grams in this case. C, specific heat, has these units to measure here. It's joules, grams, degrees centigrade. Now notice this is in centigrade. Generally, we want temperatures converted to Kelvin. In this case, it doesn't matter for this reason. If you're talking about a temperature change, a degree on the centigrade scale is exactly the same as a degree on the Kelvin scale. Remember that. Well, the only difference between the two scales is what they define as 0 degrees. But going up 100 degrees on the Kelvin scale and 100 degrees on the centigrade scale are exactly the same amount of temperature change. So as long as we're talking about a change in temperature, if we have degrees in centigrade or Kelvin, it really doesn't matter because a change in temperature is the same on both scales. So the question says water has a specific heat of 4.814 joules per gram degree centigrade. And this means that it takes 4.184 joules to heat 1 gram of water by 1 degree centigrade. So how much energy will it take to heat 10 grams of water by 1 degree centigrade? So we just use the same formula, Q. Now we're talking, instead of 1, we're talking 10 grams times the specific heat of water, so that never changes as long as you're talking about water. And that's joules per gram degree centigrade. And then that's going to be times the temperature change, which is 1 degree centigrade. So that's delta T is just going to be 1 degree centigrade. So let's check and be sure our units cancel since this is a new problem. We want to be sure units work. So centigrade cancels with centigrade, grams cancels with grams, and the only thing you have left is joules, which is a unit of measure for energy, heat energy or any other kind of energy. So if you multiply that, you're going to get 41.84 joules of energy is required to raise 1 gram of water or 10 grams of water by 1 degree centigrade. How much energy is needed to heat 30 grams of water from 10 degrees to 50 degrees? Okay, so same thing. Energy in this case means heat energy, and again, that's a scripted Q, so it may look funny to you. Maybe I can make it a little differently, but for right now, that's what it looks like. So the mass is 30 grams. And since it's water, it's still 4.184. And the delta T is 50 degrees centigrade. Your final temperature is 50 minus your initial temperature is 10. That means it's going to be a positive number, and that means in order to heat it, you have to put the energy in. Energy in means heat goes in, which means temperature goes up. All right, so that's going to be 30 times 4.184 times 50 minus 10 is 40. And that gives us 5,020.8. So that's going to equal 5,020.8 joules of energy. All right. Okay, number 35, let's try a standard calorimetry problem. So a pot of water, 2.5 liters of water initially at 25 degrees centigrade is heated to boiling at 100 degrees centigrade. A, B, well, actually this is all one question. It's really just one question. So how much energy in joules is needed to heat the water? And the density of water is 1 gram per milliliter. So we know that relationship. There's 1 gram of water for every milliliter of water. So let's use this space up here to just convert liters into grams. So that's a unit of volume. Grams is a unit of mass. But we know there's that 1-to-1 relationship for water that only exists for water. We talked about that before. So we start with 2.5 liters of water. And we know that there is 1,000 milliliters. For every 1 liter. And we know that there is 1 gram only of water. This last relationship is only for water. For every 1 milliliter. In other words, this is how much it weighs, this is how much space it takes up, and it's 1-to-1, but that's only true of water. Okay, so we've got liters of water, milliliters of water, milliliters of water. We end up with grams of water. That's what we want for our equation. Okay, so that's going to be 2,500 grams. All right, so now we can take that number and go down below and plug it into the equation. How much energy in joules? So again, energy is Q, is heat. That's in joules. The mass is, let's go ahead and always write out equations. Guys, I can't tell you how important that is because eventually you have them memorized without even trying, as long as you're willing to discipline yourself to do that every time. Write out the equation. Okay, so Q equals 2,500 grams. Specific heat of water is 4.184. You'll learn that number quickly. And that's joules, grams, degrees centigrade. And then the delta T is going to be from 25 C to 100 degrees C. So it's going to be 100. So the final goes first. It's temperature final minus temperature initial. That means it's going to be a positive number. That means the heat is going into the water, and that's what would cause temperature to go up. All right, so that becomes 75. So now you just multiply through all of those numbers. And that's going to be 784,500 joules. That's how much heat energy you'd have to put in to make 2.5 liters of water. That's not quite a gallon, but it's close, to raise it by 75 degrees. And that's how much energy right there. And then the second part asks you, what's that in kilojoules? So just use that relationship. And there's 1 kilojoule for every 1,000 joules. So you're going to divide that number by 1,000 and you get 784.5 kilojoules. Okay, what is the amount of heat released when 175 grams of water cools from 100 degrees room temperature down to 20 degrees centigrade? Again, I can't emphasize this point enough. As long as you're dealing with a temperature change, you don't have to convert to Kelvin. Let's be clear why that is. Because a degree on the Kelvin scale and a degree on the centigrade scale are the same amount of temperature change. So in the case of this problem, you're going from 100 down to 20. That's 80 degrees on the centigrade scale. But that would be going from 373 down to 293 on the Kelvin scale. So that's still 80 degrees. So it's 80 degrees on the centigrade scale. It's 80 degrees on the Kelvin scale. So it doesn't matter as long as it's temperature change. You can use either scale. All right, so what's the amount of heat released? So heat release means heat's going to be a negative number because we're taking heat out of our bank account. It's going out of our bank account. So it's going to be Q equals MC delta T. Okay, so the mass is 175 grams. We got to be sure our units are what we need. Then we need grams. Specific heat is what it is. And again, that's grams, degrees centigrade. And it's going to be the final temperature is 20. So it's 20 final, it's always T final minus T initial, or pretty much anything final minus anything initial is how you line it up. So the final temperature is 20, the beginning temperature was 100, it means it's going to be a negative number, and that means that heat is going out. When you're cooling something, the heat is being released. So just run the numbers on that. And you get negative 58,576. Be careful on the AP exam if they ask you, they might give you specific units to express it in joules, express it in kilojoules, express it in calories. Be sure you pay attention to which units. They will mark you off if you get the units wrong, even though you did the problem right. Okay, we don't always have to warm up or cool down water. The specific heat capacity of copper metal is 0.39 joules gram centigrade. So water has a fairly high specific heat capacity of 1. You'll notice that metals are much lower. They're 0.39. Aluminum or iron, I think it was 0.45. So you get these lower numbers. That means that a certain amount of heat will cause a much more drastic temperature change in metal than it will in water. So that's the effect that it has on the equation. Okay, so is it easier, more difficult to heat up copper than to heat up water? Well, your common sense would tell you what we talked about earlier, that a metal is much easier to heat up. The iron bar outside is going to get a lot hotter at 2 o'clock in the afternoon than the cup of water is. And we showed you an example in the notes of how that happens because of the different specific temperatures, that the certain amount of heat will cause a metal to get a lot hotter, to increase its temperature by a lot more than the same amount of heat will cause water to increase its temperature. So the answer to this one is it's easier to heat up copper than to heat up water. Okay, how much energy would it take to heat up 5.2 gram sample of copper from 20 degrees C to 100 degrees C? So again, these are just some pretty simple plug in the number problems. You only have one formula to work with. So energy again means heat. So the mass, it says it's a 5.2 gram sample. Specific heat, you now be sure to use it for copper. So it's 0.39 joules per gram degree centigrade. And the temperature, so it's going from 20 to 100. So it's T final minus T initial. So it's 100 minus 20. So that's going to be a positive number. That means the heat is positive. That means the heat is going in. And that's what's causing it to heat up. And that's going to be 162.24. And that's joules. Okay. if 300 joules of heat energy, notice how in this problem they put the decimal point there, meaning that those two zeros are significant. They're definitely significant in case we were dealing with that. So that's sometimes you'll see that to emphasize that point. Okay, so 300 joules of heat energy were used to heat up a 5-gram sample of copper metal and a 5-gram sample of water, both starting at 10 degrees. Calculate the final temperature of each. Okay, so now we're going to transpose the equation. It's now solved for delta T because they're asking for temperature, and that equals the heat over the mass times the specific heat. All right, so it's 300 joules of heat energy in both cases. So over here we'll have copper. And that's going to be 300 joules over the mass, and it says it's a 5-gram sample of both. And the specific heat of copper is 0.39. Okay, and so we see that grams cancels with grams here, joules cancels with joules here, and the degree centigrade is on the denominator of a fraction on the denominator of this major fraction. Means it's going to flip up and be on the top. So it's going to give you degree centigrade is going to be your final unit of measure. We'll talk a little bit more about that, but get used to units of measure being in fractions within fractions and how you work that. Okay, so anyway, it's going to be 300 divided by 5 is 60. And then you divide again by 0.39, and that gives you 153.8. So the temperature change is, for copper, is 153.8 degrees centigrade. Now we do the same thing for water. Still 300 joules, still 5 grams. But now we're talking about 1 joule per gram degree centigrade. So specific heat of water is, excuse me, it's not 1, I apologize. Thinking of something else. It's 4.184. Okay, let me just scratch that, try again. 4.184. Okay, and we will go ahead and do that. So that's 60. And then you divide that by 4.184, and that gives you 14.3. So the same amount of heat put into the same amount of mass of water gives you a 14 degrees centigrade increase, but put in the same amount of same mass of copper, going to give you 10 times as much of a temperature increase. So the copper will get really, really hot. You might not even be able to touch it. All right. Okay.